Hi, I'm Charles Dillard with Amphenol Broadband Solutions. Welcome to our Fiber 201 training series. In this training, we will cover fiber documentation. As you go through this training, the chat will be open. So if you have any questions, feel free to put those in the questions section, and at the end of this training, I will address all of those questions. So let's get started. Fiber optic documentation is more than paperwork. It is the lifeline of the network. Accurate documentation ensures technicians can build, maintain, troubleshoot, and restore the network quickly and correctly. In the cable industry, where the large-scale DAA, remote PHY, and node splits are pushing fiber deeper into the plant, documentation is more critical than ever. By the end of this training, you will understand why documentation matters, what types of documentation are required, how poor documentation impacts the network, and finally, identify best practices for maintaining and updating records. The importance of documentation becomes clear when considering the daily responsibilities of a cable technician. Troubleshooting fiber outages or service disruption requires precise records. Without them, identifying the correct sheath, enclosure, or splice tray can waste valuable time, delay restoration, and extend customer outages. Documentation also prevents accidental mistakes such as splicing live fibers or cutting into the wrong route, which could worsen the outage or create safety hazards. In addition, documentation reduces unnecessary truck rolls and wasted materials. Customers benefit from reliable service and faster repairs, and the company avoids penalties associated with service level agreements. Finally, documentation serves as a future-proofing tool, helping technicians and engineers make informed decisions during network expansions or upgrades years after the original build. Fiber optic documentation takes several forms, each serving a distinct purpose. Route maps illustrate the physical pathway of aerial, underground, and in-building fiber runs. They often include GPS coordinates or CAD-based layers that identify splice enclosures, pedestals, manholes, and handholds. Splice documentation details the layout inside each enclosure, showing tray assignment, splice orders, slack loops, and fiber color coding. Proper labeling conventions such as using sheath IDs and fiber counts tied to the destination points are critical for consistency. OTDR and test records provide a baseline of performance, capturing insertion loss, reflective values for each fiber at the time of installation. These results become vital reference point for troubleshooting in the future. As-built drawings reflect the network as it was constructed, capturing field deviations from engineering plans. Finally, work orders and change logs record all subsequent modifications, from node splits and remote PHY deployments to emergency splicing during outages. Splice documentation details the layout inside each enclosure, showing tray assignment, splice orders, slack loops, and fiber color coding. Proper labeling conventions such as using sheath IDs and fiber counts tied to the destination points are critical for consistency. OTDR and test records provide a baseline of performance, capturing insertion loss, reflective values for each fiber at the time of installation. These results become vital reference point for troubleshooting in the future. As-built drawings are construction maps that are updated after build completion, and they reflect exact field changes, not just engineered design. The documentation workflow follows the life cycle of a fiber build. In the design phase, engineers create high-level plans that define fiber routes and splicing assignments. During construction, contractors and technicians capture as-built conditions and deviations from designs. At turn-up, test results such as OTDR traces and power levels are documented and archived. During the maintenance phase, every new splice, cutover, or node split must be recorded to ensure documentation remains current. Finally, during restoration, technicians rely on these records to quickly identify priority fibers, reference splice locations, and restore services efficiently. Unfortunately, many networks suffer from poor documentation practices. Maps often go out of date and no longer match field conditions. Splice diagrams may be missing from pedestals and manholes, leaving technicians guessing. Incorrect color coding, missing labels, absent test results further complicate troubleshooting. Sometimes emergency restorations are completed in the middle of the night, but not properly recorded afterwards, leaving gaps in the records. The results of these issues delay repairs, higher operation costs, and frustrated customers. The cable industry uses a variety of tools to manage documentation effectively. Geographic Informational System, or GIS, provides spatial mapping. Fiber management platforms track splices, fibers, and routes in detail. Barcoding and RFID tags are increasingly used to label enclosures and reels for easier tracking. Mobile applications allow technicians to update documentation direct from the field, while standardizing label kits ensure uniform fiber identification across the network. 20 years ago, fiber documentation in the cable industry was largely manual and fragmented. Most record was kept as paper as-built, CAD drawings, or Visio files stored on local servers, often updated weeks or even months after construction. Field data collection was done with clipboards, hand sketches, and basic cameras, requiring entry into the office. Location accuracy was limited, typically within 5 to 10 meters, using hand-drawn offsets or consumer-grade GPS units. Labeling and identification were inconsistent. Many crews used an ad hoc naming system or Excel sheets that didn't align across the regions. Color codes followed printed charts and personal experiences, which led to mismatches and confusion. In 2025, fiber documentation has evolved into a fully digital and connected ecosystem. Modern cable operators use telecom-grade GIS platforms to maintain a live digital twin of the network, showing every fiber, splice, and connection in real time. Field data is collected through mobile apps with offline mapping, validation, and automatic synchronization to central systems. GPS accuracy has improved dramatically, with crews using receivers capable of centimeter-level precision for locating handholds, closures, and splice points. Labeling follows standardized convention, ensuring every port, panel, and path can be traced consistently. Color coding is now standardized, eliminating confusion across the bills. Splice documentation was physical, with paper schematics and messy bird's nest diagrams and binders. Test results from OTDRs and power meters were printed and filed by job. Asset tagging relied on handwritten notes, stencils, or metal tags that were often lost or illegible. Photos were optional and stored in CDs and personal cameras, rarely linked to the actual network record. Change management was slow. Updates were made as built after the fact, often long after the network was in service. Restoration efforts depended heavily on local technicians' knowledge and paper maps, making outages time-consuming to isolate. Each department, whether it was construction, operation, network operation centers, and sales, maintained its own files, creating silos and inconsistencies. In 2025, splice points and metrics were stored digitally, often embedded OTDR traces and photos and test results tied directly to GIS assets. Test documentation adheres to IEC standards and is automatically uploaded for acceptance and Q&A. Assets in the field, closures, cabinets, and tools are tagged with barcodes, QR codes, or RFID labels, which link back to GIS or work management systems. Photos are mandatory, geotagged, and timestamped, providing full visual traceability. Change management happens in real time, with version control and audit trails for each network modification. Restoration is now data-driven. Technicians can trace fiber path instantly, check stored loss budget, and isolate faults faster. Cross-team visibility is seamless as GIS integrates with work management inventory and outage systems, ensuring all departments operate from a single source of truth. And finally, let's talk a little bit about best practices. Best practices for technicians revolve around consistency and discipline. Technicians should always verify splice labels before cutting or working inside an enclosure. Any changes made in the field should be recorded immediately. first in field notes and then submitted to ensure the official documentation system is updated. Taking photos of enclosures, trays, and slack storage provides a valuable visual record for future reference. Consistent naming convention for sheath, fibers, and enclosure eliminate confusion. During restoration events, technicians should carefully update records to reflect fibers were respliced or rerouted, preventing future techs from repeating the same discovery process. In closing, fiber optic documentation is more than paperwork. It is the lifeline of the network. Accurate documentation ensures technicians can build, maintain, troubleshoot, but more importantly, restore the network quickly and correctly. That concludes this training on fiber documentation. I see that there's some questions that's come in, so I'm gonna walk over to my computer and we'll begin answering those questions shortly. Okay, welcome back everyone. Just looking over here, I see there's two questions in the chat. The first one from John, what do you look for when selecting the right GIS software? Well, it's been years since, I've been out in the field, and back then a lot of, stuff that we use was more like documentation. But, with current ways of documenting a fiber optic network, after you decide, cost versus the value that you're getting for the software, probably one of the biggest thing would be like, it's important that the software is detailed enough to show you every point that light level will travel. So, most GIS software will have, the street view, but they have to be able to show stuff like enclosures and pedestals, stuff like that, because when it comes to, fiber optic, as you know, you have to be, able to pinpoint locations, especially, during times of like restoration. Another thing, sometimes you may not have, Wi-Fi or whatever. So if you have access in the field to the GIS system, sometimes there may be a need to download certain segments of the routes in case you were to lose some type of cellular or, Wi-Fi signal. So a big benefit would be, are you able to download the software that you're leveraging? But then more importantly, I know newer software, they have the ability to where you can make changes within the software. There's a term for it, digital redline or digital redlining. Like in the past, if there was any changes, you would, mark it up, on a map or whatever. And then when you would get back to the office, you would do the updates. But current software allows the ability to actually make changes within the software itself, which will, help to make sure that the information is, accurate. Because, we're humans, sometimes we have the intentions of making those updates later, but then life happens, another outage may occur or whatever the situation. So those would probably be some of the top things I would look for in selecting software for your documentation. Another question, while the topic is not directly related to documentation, which OTDRs are generally regarded as reliable and industry standard for fiber testing? Believe it or not, really anything that's on the market nowadays is very reliable. With our training, we don't get into like particular vendors or manufacturers. But the one thing about your question, though, which I like, is that understanding that with an OTDR, it's going to show you distances. It's going to show you the events that are happening. It's going to show you the losses and reflection, etc. But that's just one part of the whole how important documentation is, because that OTDR is not going to tell you what enclosure that you need to be driving to. It's not going to tell you which tray that particular fiber that may be causing that that small outage or whatever is located. So it's going to be a combination of using, an OTDR and other test equipment, along with having accurate maps. So I guess to answer your question, you know, uh, any OTDR that's on the market that most cable companies and MSOs are using is going to be adequate. Again, you get what you pay for. So again, you want to, like I mentioned earlier, take a look at what the cost is versus the value that you're getting with that particularly either software or, in your question, hardware. So great question, Mike. Hopefully that answered it. The next question from Matt: top 2 or 3 things people get wrong about documentation. I wouldn't say get wrong, but what I would say is that when it comes to documentation, uh, sometimes we may think that we're talking about the software that the NOC is leveraging to get the information to the technician. So like the GIS software, but also documentation means, does that information in that GIS software, does it match the information that's on that splice enclosure? Does it match up there? Does the information in GIS as it relates to which tray actually matches the tray that particular fiber is enclosed in? And then also the fiber count. Does GIS say it's fiber count 12, but when you get there, that fiber is actually fiber count 15 or 24 or whatever. So making sure that documentation is consistent throughout the network, because at the end of the day, light or that signal is really invisible. So you have it leaving and it's going, many, many kilometers. But when we overlap it with a physical map, then distance doesn't mean a thing if the technician doesn't have somewhere to go to, like an enclosure or, where your slack is stored, et cetera. So that would probably be one of the biggest thing about what people tend to get wrong about understanding documentation. The other thing, I mentioned it briefly, probably should have spent a little bit more time on, which is the importance of as-built. When you look at a particular design of whether it's a fiber optic network or a coax network, when engineers get together and they map it out, and here's where the slack should be stored, here's where we should put the whatever the equipment is, whether it's an enclosure or cabinet or depending on your architecture that you're deploying, you have that design. But in real life, sometimes we get out there and we can't place equipment in those locations because of some obstruction. So we have to, reroute things. But it's very important to take that information and get it updated in your software, because your software is only as good as what's happening out there in the field. If you think about something as simple as you come home from work, or you're getting ready to go to work, and you put your keys on the kitchen table, and you get a phone call, so you walk away, and one of your kids grabs your keys and moves it into the living room somewhere. Even though that distance is really short and you're not having to cover a lot of ground, but finding those keys can cost you an additional 5, 10, 15 minutes of delay searching for it, because it's not where or thought it should be based on your encounter at that moment. But when you leave the site and come back and it's not there, and similar with when it comes to as-built, on the design map, whether the fiber optic is already there, but during times of storms and accidents that happen within the network, and sometimes you have to move pedestals and enclosures and whatever else, maybe 50 feet from where the map shows it should be, or sometimes even longer. So making sure that those as-built and things that happen in real life actually get put into the software is very important when it comes to documentation. So those two things are, what I would say that some people may not see or really understand the importance of making sure your documentation is consistent in the software, as well as the labeling on the devices out in the field, and then also making sure as built and any type of changes in the real network has been updated in the software. And then there's a question from Gary. Is there a download of parts 1 through 4 of this presentation? So great question. And that kind of leads me into the plug I always do at the end, which is on December 30th, we will be doing our final installment of our Fiber 201, which will be fiber to the home troubleshooting. So we'll take a look at everything that we've looked at from the 4 previous training, which was fiber math, test equipment, fiber restoration, and then today's training, which is documentation. So we'll take a look at everything that we learned and then apply it to actually troubleshooting a fiber to the home network. And which we will get into how do you troubleshoot if it's affecting one customer versus multiple customers, and where in the network should you leverage those tools that we learned about to do all your testing. So Gary, after the fact, we will have all 5 of these training series on our YouTube channel. And we will be sending out messages about that via LinkedIn and our YouTube channel as well. So great question, Gary. Thanks for even wanting to download those parts, and hopefully you're finding some value in these micro learning for fiber optics. So with that, again, I want to thank everyone for joining, especially on a Friday. You could have been anywhere, so glad that you chose to spend a few minutes with us and talk a little bit more about fiber optics. And we look forward to seeing you on December 30th to talk about fiber to the home troubleshooting. And with that, have a great week, and we will see you next time.